Our first speaker is going to be telling us about dependent coeffects for local sensitivity analysis. So this is Victor Sannier. Can we get his slides? Yep, okay. Go right ahead.
Thank you for the introduction. So I'm going to talk about a notion we have introduced, which is dependent coeffect, in the context of local sensitivity analysis with applications to differential privacy protection. So I am first going to talk a bit about global sensitivity and why is it useful in the context of differential privacy before moving on to some type systems that have been introduced to analyze sensitivity and the links it has with linear logic. And then we will move to dependent coeffects, which are our main contribution before giving a few case studies. So first of all, about privacy for our motivation. The setting we're considering is the following. So you have a data analyst who sends queries to a database, and we want to be able to answer to queries that are for general concern. So if it's the mean, the median, the standard deviation or whatnot, we should be able to answer those queries, but not targeted ones. And to do that, just removing all the identifiers or strictly personal informations about the data in the database is not sufficient, as you all know. So instead, we would like to have a formal definition. And the most popular one is the following. It's differential privacy. The main idea is that the result of a query should be roughly the same for D and D prime, being two databases that differ by only the presence of absence of a single individual. So if you know everything about a database except that one single person is absent or not, you cannot learn anything, basically. So formally, you have some privacy parameter epsilon here, which acts at the maximum multiplicative difference between the probability of queries satisfying a predicate in either case. And one of the main reasons we study this property is because it is composable. So if you know that two queries are differentially private, then you will know their composition is 2 for a very wide definition of composition. So we can talk about sequential composition, parallel composition, and so on. So it's a very nice property to work with. And one way to make an arbitrary query preserve differential privacy is to first study how sensitive it is. So how much does the output depends on the input. And we can study that in fact, a very general setting. So if you have just a function between two metric spaces, you can always define this quantity, which is the maximum multiplicative impact of given two arbitrary inputs. So for differential functions, this is essentially an upper bound on the absolute value of the differential. So here are just two small examples. For a linear function or a fine function in general, this is going to be the multiplier component. And for, multiplication or the square function and so on, is going to be infinite, since there is no way to bound that arbitrary without taking a specific point into account. Okay, and once you know that, you know this quantity, you can make a query private by just adding enough noise, and the noise is going to be calibrated on the sensitivity. So if the function is very low sensitive, let's say it's a constant, you don't have to add any noise in order to make it private. It's already private. But if it's the identity function, then you're going to have to add a lot of noise. So the example theorem I put there is the Laplace mechanism for real value queries, but of course there are many more ways of doing the same kind of thing, and there are many theorems in the literature. Okay, so that was it for the introduction about privacy in general and sensitivity in particular. And now I'm going to talk a bit more about type systems and ways in order for ways to bound this quantity. for functional programs. So what Reed and Pierce did in 2010 is to notice that judgments which are very similar to those of linear logic, except from grades, real valued grades, can be interpreted as a sensitivity property. So you just take a typing judgment, you add real values to all variable type pairs, and it can be interpreted as to mean a sensitivity condition. So here are a few examples of sound judgments. The first one say that a linear function in two variables, it does a number of times each one is used, as in linear logic. For the square function, as I was saying earlier, it's infinite sensitive in X. And if you want a more complex example, because in their language you have recursive data types, you can deal with lists, for example, and sorting is actually one sensitive. And you can prove that in the system. Okay. As for the semantics, it is what you expect if you have some knowledge of the categorical semantics of linear logic, meaning you have category with all your products, coproducts, and so on. And the main point is you have a compatible graded comonad. So this is the main thing that does the annotation, essentially, the real value annotations. And the category of metric spaces is one such category. So it is a model of fuzz and the intended model. Okay, it can be lifted to metric complete partial orders to deal with recursive types and so on, but I won't go into that. So here is for the state of the art. Our goal now was to go beyond this notion of global sensitivity and to design a corresponding type system. The main issue is that it is often infinite. I get the example of the square function, but it's also the case for a number of useful queries. And the reason intuitively is asking for uniform bound on this quantity is way too strong. And actually, in practice, we are only interested in the sensitivity at a very specific point, which is the real data set. So instead, we're going to study local sensitivity, which I'm going to define formally in a minute, but intuitively it's just a sensitivity, but at a given point. So instead of considering the Lipschitz constant, we're considering the derivative, in a way. And it's interesting to study because it also can be used for differential privacy. It is slightly more complex. You have to use frameworks such as PTR. There are also other ways of doing it, but the only thing to know for today is that it is also useful in the context of privacy preservation. So the notion of local sensitivity we are studying is a bit more general than one found in the literature. We are considering sensitivity at point X, and here is our novelty, at radius K. For otherwise, we won't be able to compose the sensitivity, but the details don't matter that much. We're asking that for any point in a given radius, so for every x prime such that the distance with x is smaller than a given radius, then we have a bound on the output of the function. So we have a bound on the distance between f of x and f of x prime, just as before. So the reason we introduced this is to be both a reasonably low approximation of the local sensitivity used in the literature, that is with k equals 1, but still being composable. And just as an example, for the square function, you get 2xk, so k being the radius and x being the point, which is very similar to the derivative, as we expect. Okay, so here is the type system we considered and we introduced. So the types are pretty much the same ones as fuzz, except that the annotations are very different. Before, the annotations were real values. Now they are functions, and not trivial functions. So I will spend some time explaining what's going on. You have two. So you're taking a value as first argument. Then you're taking a number, which is a radius you're considering, and the output is going to be some sensitivity value. And we also require some syntactical properties to hold, such as monotonicity in the radius, this kind of stuff. So these are going to be our notations on arrows. And in here we say that these coeffects are dependent because the grades of coeffects you can attach to a type tau depends on, it's not the same for every single tau, basically. Whereas in fuzz, the coeffect for tau would be the same as the coeffect for sigma, would be, and just real values. Okay, and now we can consider considering judgments as follows. So we have a pair of, a set of pairs of variables and types plus a coeffect, a global coeffect. Here S, I mean a context-wise coeffect rather, S, which is a function that takes all the values, all the radii, and gives you back a number. And the reason we do not add a coeffect to every single variable as in fuzz, but instead in a context-wise manner, is just to have better bounds. But from a purely theoretical point of view, we could also do like in fuzz. It's just way more precise in this way. For example, we are able to type multiplication, which doesn't seem that impressive perhaps, but it's infinite sensitive when we consider global sensitivity. So it's nice here to be able to give exact values. And I will give the typing judgments a bit later. Okay, so here are the rules. I mean, a subset of the rules. So, you know, to type a variable, you have to give 1 as a coeffect. Okay, it's a bit of a special one, but the idea is that you do not depend on the value x, and you just, if your inputs are at distance k or bounded by k, then your output is also bounded by k. So it really acts as our 1 here. For tensor introduction, you just have to add the two functions pointwise. For function introduction, it's a bit more interesting because in order to abstract a variable, you have first to put the coeffect in the correct form. That is as a sum of two coeffects, one of them associated with gamma and there was one associated with sigma, meaning you first have to apply weakening. And this can be very costly. During introduction, you may introduce infinite sensitivities, but this is what it is. And for elimination, so here is our elimination, but more generally for all the elimination rules, you have to consider some kind of scaling, as in fuzz. But here the scaling depends on the term you're considering. So it's kind of, I used a scaling notation, but it's more like function composition under the hood, but should be interpreted as scaling. Anyways, and we have also introduced other operations on coeffect to deal with, for example, disjoint sum and so on. And one nice feature and a reason to believe that we're doing something at least somewhat sound is that we can subsume fuzz, meaning that if we only deal with specific functions that mimic the behavior of fuzz, meaning just linear combinations of the radius of the radii and not dependent on the point we're considering, this perfectly encodes fuzz. On all our typing rules, just become fuzz's rule. So we completely subsume fuzz here. Okay, and as I was saying a bit earlier, we can also add typing rules for all kind of primitive operations, so operation on list and so on. But the one I want to show is just multiplication. It can look a bit scary at first, but you can notice that it is just saying that it is the first term times the difference in the other one, plus the second times as the distance in the first one, plus the multiplication of the two distances. So it's very what you would expect, and it's quite intuitive after some time. And we can derive the exact sensitivity of the square function, to take our example again. Okay, so let's talk a bit about the semantics. It is almost, the base is the same as in greedy linear logic, meaning you have monoidal class categories with your reckoning, coproduct, and so on. And the novelty is to consider a graded, a dependently graded comonad. So this was introduced recently in 2024 in a quite different setting. And to the best of our knowledge, this is the first work considering it from the point of view of a type system. And we think it can be useful in a variety of contexts, but here at least is in the case of local sensitivity. And given this semantic interpretation, one of the main results, semantic results, is that if you can type a term E with some annotation S, what you obtain is a bound on the sensitivity, on the local sensitivity of E at any given point you choose. And here I specialize to the case k equals 1 because it's the most useful one in practice. It is the one already known in the literature and so on. And the conclusion you should keep in mind is that if you are able to type a query, then you know how to make it differentially private. Okay, just to be somewhat concrete, I will give a few case studies. So first of all, I will go back to global sensitivity because being able to derive a local sensitivity as intermediate steps can be useful. And afterwards, I will talk a bit about something more specific. So first of all, global sensitivity analysis. If you consider judgments which do not depend on the value, so here is such judgments. They can have a variety of forms, but this is the one that encode first, for example. You can consider other ones. What you get, in fact, is a bound that does not depend on the point you consider, so it is a bound on the global sensitivity. And what we showed with specific examples is that it's not uncommon for the bounds on global sensitivity to be better than the one we obtain in first. So being able to first talk about local sensitivity, to talk about some compensation stuff, allows you to at the end use standard techniques such as the Laplace mechanism, but with less noise, which means more accuracy for the same privacy guarantee. Okay, and the second example I want to talk about, which is perhaps more specific to local sensitivity, is some simple algorithm I want to show you how to type. So let's consider that we have just a bunch of numbers, let's say normally distributive numbers, and we want to find an interval containing 95% of the values while preserving differential privacy. So a way of doing it, there are many ways, but this one had the advantage of using only a single primitive, is first to compute the mean, which is equal to the median, and then to compute the standard deviation by using some multiplicative factor of the difference between the quartiles. Doesn't really matter, this is just a way of doing it, that's using just quartiles. And at the end, you return the two numbers you're interested in. So the only primitive we need, as I was saying, is a quartile. It is already well known that you can give this formula for the local sensitivity of the quartile, and consequently you can add a corresponding typing rule in the system. So here it is. And using this rule, what you can derive is that function I have just written, typical range, is taking a set of integers, giving back a pair of integers, but with some special annotation S, which is a function from the point in the radius to a quantity, which if you take a closer look at it, closely resembles the structure of the programs, as you would expect. But there is 2 times the local sensitivity of the second quartile because we're using that twice, one in each coordinate of the result, for example. So it's very close to the structure of the program. But what is most important to notice is that it is finite. Whereas in Fuzz, the best we could write for even the quartile would be infinite. And now what we can do is apply any framework we want that takes a query and a local sensitivity bound as input and gives you back a new query that behaves almost exactly the same, apart from generating some noise, adding some noise to it, and you get back a privacy-protecting version of it. Okay, so let me conclude with first a summary of what we did. So what we have designed is a type system for deriving some upper bounds on the local sensitivity of functional programs. And I've shown how it can be applied to differential privacy. And about future work, one of the main points to notice is that our calculus is quite non-specific in its syntax. What I mean is that I expect that apart from the definition of the semantic definition of the operators and so on, maybe the specific grades we use, because it was function from a value to a number with some syntactic restriction, but using a different grade, I think we can apply this methodology of dependent coeffects to a wide variety of problems, including maybe time complexity and information flow control. So if you have some ideas about that, I would be more than happy to discuss. And another direction is to study type checking, because the constraints we would be considering while writing type checking algorithms are quite difficult, because we are dealing with functions all the way. So, we use only a subset of all possible functions and so on. But since we have reckoning, I think it is quite a difficult problem. And once again, I will be more than happy to discuss that. So feel free to ask if you have any question.
Okay, we have time for a few questions. Yes.
Yeah, thank you for the talk. So, because it's still on the slide, so other dependently graded comonads, do you have some at hand, some in mind?
So yeah, are there also examples of dependently graded comonads?
Yeah, so what comonads do you have in mind there? Because
okay,
you mentioned cost specifically, but
so what we're requiring is essentially the grade to be able to depend on the object. So we have a different grade for each possible object.
Sorry, do you have examples of those? More examples that you're excited about?
Yeah, there are more examples in the paper that introduce the notion, but I don't have like easy, specific computer science relevant example at the end. So.
Okay.
Yeah.
Okay, we have time for another quick question. So I'll ask real fast. Can you tell me a little bit more about what would be involved with decidable type checking? Like you mentioned the complexity of the constraints. How practical do you think it would be?
I think the main issue is the line you draw with reckoning. So we have a reckoning world and that depends on inequality relation between coeffects. And depending on how loose or how strong it is, it can become very subtle. Like even for subject reduction, we have to be very careful about the hypothesis of our inequality relation. And I believe, for example, that if you take arbitrary, just semantically valid reckoning, then it becomes quite clearly undecidable, I think.
Okay, thanks. Sounds challenging.
Yeah. Thank you.
Okay, thank you very much.